Yes, Shalini.
Yes, sir. May I
Begin.
start, sir? Dear all, good evening. Today we gather here for a special occasion that is the International Expert Talk Show on
One
the
minute, one minute, one minute,
topic. Hanji.
1 minute. I will interfere for a
Okay.
moment. Uh,
Yeah, sure, sir.
let first Prathamesh to start the recording because we
Okay.
want to record our lecture. So Prathamesh,
Sir,
will
I
you
have
start the
started.
recording? Okay, okay. Thank you, thank you. Yes, you start now.
Okay, thank you so much, sir. Dear all, good evening. Today we gather here for a special occasion that is the International Expert Talk Show on the topic Bioprocessing of Secondary Metabolites, Current Challenges, Emerging Opportunity and Future Outlook, which is organized by the Microbiology Society, India. Today, we have with us our resource person, Professor Dr. D.K. Acharya, the Head Department of Microbiology and Biotechnology, Gandhinagar Institute of Science, Gandhinagar University, Gujarat, who has accepted our kind invitation to share his knowledge and expertise on the concerned topic. We are highly thankful to the organizing board members, firstly, the chief patron, Professor Dr. Arvind M. Deshmukh, founder and All India President of the Microbiology Society India. Secondly, the executive convener, Dr. Ajay Kumar Srivastav, an associate professor and the head department of botany, St. Xavier's College, Autonomous, Ranchi, Jharkhand, and the organizing chairman, Mr. Sharath, the national representative of Microbiology Society, India, who helped us in arranging this international expert talk show and gave us with the wonderful and exhilarating opportunity to be a part of this seminar. Dear all, as we all know that any event is not going to be a successful without praying to the God. Therefore, I, Ms. Shalini Mishra, Assistant Professor and the Organizing Committee Member of IETS BSM 2025, your today's host of the event, want to commence this program with a prayer service. Let us bow our head and put ourselves in the holiness of God the Father, the Son, and the Holy Spirit. Dear Almighty and ever-loving God, we glorify and thank your name. You have showered us with so much blessings, and your presence continuously reminds us of your faithfulness and guidance. May we humbly ask you to shower our speaker today with your greatest inspiration so that he may share the most of his knowledge, his field of expertise, and his respective topics. May we also absorb the invaluable knowledge and experience and put them into practice that we may learn today. Your infinite blessings would mean the success of this seminar. May we be a living witness of your genuine love through the enactment of the knowledge acquired throughout this activity. We ask this in the name of Jesus Christ, our Lord and Savior. Thank you. Now, ladies and gentlemen, let us now welcome our chief patron, Dr. A.M. Deshmukh, former professor and head department of microbiology, Dr. Babasaheb Ambedkar, Marathwada University, Sambhajinagar, and President, Microbiology Society. Secondly, the executive convener, Dr. Ajay Kumar Srivastav, an associate professor and the head department of botany, St. Xavier's College, Autonomous, Ranchi, Jharkhand. He is also the former internal quality assurance Cell Coordinator in charge of the St. Xavier's College and Autonomous College of Ranchi University. Also the state president of the tenure 2021 to 22 of the Microbiology Society India Jharkhand chapter and the current All India Executive Convener of the Microbiology Society India. Dr. Srivastav is also the Jharkhand State Director of the Global Forum for Sustainable Rural Development. Sir is also the chairman of the International Academy of Science and Research, chairman of the International Foundation of the Environment and Ecology, and chairman of the International Benevolent Research Foundation of the entire Jharkhand state. And next, the organizing chairman, Mr. Sharad Subra, the national representative of the Microbiology Society. I welcome you all in this seminar, sir. Over.
Over to Deshmukh, sir. Sir, please.
Thank you. Thank you very much. In fact, every time I'm attending your seminar only for the reason I want to encourage the attempt or efforts you are taking for boosting the knowledge in microbiology and popularizing microbiology subject throughout the India. Today also, I'm surprised and happy to see that more than 100 participants are there, attendees are there. And today's lecture, Dr. D.K. Acharya, who is one of my very good friend, he will be delivering lecture today. So I request everyone to attend the lecture. I thanks my friend Dr. Ajay Kumar Srivastav, as well as a student representative, Paine, Mr. Paine, and today's anchor. She has done an excellent job in introducing this event. Thank you very much.
Over to Ajay, sir.
नया बनवाता फिरेगा वो टिप्स पैर मम्मी का सामने लाऊंगी कुट्टी लाऊंगा एक खाने देवा ना कि खाते तो यही देते ना अच्छे मंगे वाले
Hello.
तो बार
I think sir is having some issue with the mic. So whatever the wishes is there, he will type in the comment box.
Maitri, please continue.
Good evening, everyone. I am Miss Maitri Alpesha, hailing from Gujarat state of India, currently pursuing BSc Microbiology from Parul Institute of Applied Sciences, Parul University, Vadodara, Gujarat. It's my absolute honor and privilege to introduce today's research person, Dr. D.K. Acharya. Dr. D.K. Acharya is a distinguished microbiologist renowned for his significant contributions to field of microbiology, particularly in the areas of medical microbiology and industrial microbiology. Currently, he serves as a Dean Research and Head of Department of Microbiology and Biotechnology at Gandhinagar Institute of Science, Gandhinagar University, Ahmedabad. Professor Acharya's career focuses on researching the secondary metabolites production from actinobacteria, microbial infections, antibiotic resistance. He has been a leading figure in understanding the role of microorganisms in both human health and the environment. His research has contributed significantly to the development of strategies to combat the microbial diseases and improve public health. Throughout his illustrious career, Professor Acharya has published articles and has actively contributed to academic growth through his research in medical microbiology and biotechnology. His work has been widely recognized with numerous citations across research journals. He has also successfully led several research projects focusing on the applications of microbiological principles to address both healthcare challenges and environmental concerns. He has 5 patents on his name. He handled the project on bioplastic production from agricultural waste. As an educator, Dr. D.K. Acharya has demonstrated a deep commitment to mentorship and student development, fostering a collaborative and a dynamic academic environment. Currently, 3 PhD students work under his guidance. His leadership in academic sphere has encouraged and inspired students and faculty alike, contributing to the overall advancement of microbiology field. He is known for his hands-on approach in teaching, often integrating real-world applications of microbiology into his lessons. In addition to his academic responsibilities, Professor Acharya is actively involved in various scientific societies and conferences. He regularly presents his research findings at national and international events, sharing his insight on secondary metabolite production and its impact. He also serves as a reviewer for prominent scientific journals, ensuring that the highest standard of research are maintained in his field. Overall, Dr. D.K. Acharya is a respected figure in the world of microbiology with a reputation of his research excellence, academic leadership, and commitment to mentorship. His contributions to the field have a lasting impact on both scientific community and the education of future microbiologists. Sir, we are highly grateful to have you here with us. Over to you, sir.
Thank you very much for giving me an opportunity over here to present my ideas about this today's topic. Uh, I am grateful to Dr. Desmukh sir, Dr. Ajay sir, and Paine sir for giving me an opportunity to present my views on current topic, which I am going to present today's lecture. So I am thankful to all 3 people who communicated with me regarding to this. So I hope so. Now I am going to start my presentation. So please, sir, please kindly allow me to share the presentation. Fine, sir. Yeah, thank you. So is it visible to everyone?
Yes, sir, it is visible.
Yes, sir, visible.
Okay. So today my topic is bioprocessing of secondary metabolites, the current challenges, emerging opportunities, and the future outlook. So first of all, why I choose this topic? That is the important thing for me to choose this topic. That is the recently I completed one of the project regarding to the production of bioplastic right now for the 4 months. Okay. So I thought that this is the current scenario and the current demand of mankind to address this kind of a thing uh, for the benefit of the nature. So I choose this topic to present my views on this secondary that there are the lot of microorganisms are there. They are producing a secondary metabolites. But the important thing is the history about this thing. It started back to the we can say the end of a 19th century and in the starting of the 20th century. In this at that time, the First World War and the Second World War was going on, and because of that thing, the lot of new discoveries happened at that time. During these discoveries, the one of the most prominent and we can say the golden discovery was the discovery of the penicillin. So when the penicillin was discovered by the Alexander Fleming, but at that time they produced only in the liquid form. But uh, how to use in the war era, that is the questionable. And after that, in 1943, the Chain Weizmann actually started the production of this penicillin by the fermentation technology in deep fermentation technology. And since that, the secondary metabolite production was the revolutionized the mankind history. Suddenly, after the COVID-19, there was a sudden booming in the global bioprocess technology market, and it will raise around 55,841 million market by the 2030s. That is, I can say that the thanks to the COVID, the everyone now believing that there are the certain organisms are there. They actually the play an important role to save the mankind, and they have some good quality for the benefit of the human being. So I choose this topic because of this thing. Generally, the global market technology right now, uh, Europe, America, and some East Asia, Asia, we can say, using the bioprocess technology, and they have a more advanced technology. And generally, these are the involved, the bioprocess market involved in the hospital, research lab, and some medical institution. So generally, these are the scope where the bioprocess technology are using. The bioprocess technology, uh, market analysis, we can see that generally the highly utilization of this market or incorporate this thing in biopharmaceutical industry. They are producing the vaccine, drugs, some hormones. So this is the main aspect, and because of the sterility, the we can say the fermentation technology are the most challenging part in the pharmaceutical industries also. Other than this, industrial chemicals are important over here. which produce some industrial grade and environmental management is another way to tackle some environmental problem. But right now, what is the need of an hour? We can say the plastic is generally we can say is a chemically produced and it increase the global problem as we know and so the current concern about the surrounding environmental pollution caused by the discarded petrochemical plastic have problem created problem and because of this thing it promote the biodegradable plastic material research. And we know that the certain microorganisms have a tendency to produce this biodegradable material inside their cell in the form of a reserve food material that is we known as a PHA, that is a polyhydroxyalkylenate, PHB, polyhydroxybutyrate, polybutylene succinate, PLA are the regarded as a major alternatives for the traditional petrochemical plastic. So this is the most important thing. If we see the few statistical things in 2017, the plastics was recycled only the 9%, 12% was incinerated, and the 79% plastic present in the landfill and the ecosystem. So it ultimately increase over here in the form of we can say it increase the pollution in cause the environmental hazard. So the extensive use has result in a pollution, depletion of various resources like crude oil, increase the carbon dioxide emission, as well as the uh, we can say the cause the heat also. So plastic being the non-degradable in nature and affect the flora and fauna. So the we need some alternate. So the what microbes can do in the nature, the microbes accumulate the PHA as the way to survive under a stressful and the unstable environmental condition. This is the beauty of the nature. The organism when get a adverse condition in the stressed condition, they produce or accumulate this PHA or PHB. And we are using this for the betterment of the humankind. The PHA is synthesized by the many organisms, but when during the unbalanced nutritional condition. So the commercial production of the PHA is a far from the being able to meet the market demand because the microorganisms are very tiny and they produce in very less quantity in very minute amount. So the we can say when we need a huge amount of alternative of a plastic, we need a huge amount of a production of a this plastic. So notably, here the high production cost of the PHA that is 2.2 to 5 euro per kg is actually the we can say the when we compare to the traditional plastic, it is a very high amount. So this is one of the my important thing I would like to say that here is a one kind of a you can say the case study for the production of a secondary metabolites. So this one is organism is produced during the stress condition in the secondary phase of a and as we know that the organism generally produce all the secondary metabolites during the secondary phase of their growth that is the log phase and after the completion of the log phase, the suddenly the stabilized condition will be there for during the growth phase of an organism, and in the later stage of a stationary stage of a growth, the organism which produce this bioplastic or these secondary metabolites, they utilize by themselves for the survival itself. And during this phase, the organism produce a lot of different things also, like some antibiotics for the survival. They produce some proteins, some enzymes. These are the secondary metabolites. So, but right now I am presenting this one type of a case of a production of a PHA. So you can be aware about this thing. So as I am not going to deep in the discovery of a PHA, and first time it was observed by the German microbiologist Kurt Schon in 1920, observed the bacteria can produce this PHA, and since that the lot of work uh, done in this field, but the modern advancement and the commercialization is the most important. Right now, the many companies are there, they are producing these secondary metabolites, that is the bioplastic, in a large scale. For example, Dynamia Scientific, CJ Bio, and the Kaneka. These three are most important uh, companies who producing this bioplastic or PHA. And if you can search in website, this try to find out. I am telling each and every participant over here that try to find out the some statistical data, the company profile, the amount they are producing. The bioplastic is a huge, and where they are using a very very advanced system for the production of this PHA from the microorganism. As a microbiologist or biotechnologist or life science people, we have to know the role of the microorganisms, and these are companies in their, I can say there in their financial aspect, there were no microbiologists right now. Then also they are using secondary metabolite production for the betterment the human being as an alternative source. So you can see, and what they are trying to produce from where they are using the agricultural waste. What we are studying in our courses, the utilization of some agricultural waste and convert this waste to the some important valuable product, they are really applied for the production. So this is a common biochemical pathway for the biosynthesis of a PHA. Generally, there are the PHA, PHAB, and the PHAC. These three enzymes, these three point are critical point, and these three are actually the genes. They are responsible to convert the sugar or a carbohydrate source to the PHA and PHB. So these three genes are most important. How can we start any kind of a secondary metabolite production? First of all, we need to collect the sample. Second thing, the screening. We need the here I'm showing this is the pathway, the sample collection, the isolation, and the enrichment of some organism. I worked on the some thermophilic organism, so I mentioned over here the selection of a PHA producing colonies. You can see the screen when we try to screen the organisms over here, the bioplastic producing organism accumulate the PHA and it shine in the under the ultraviolet radiation. So this is this one. Then we have to produce, optimize the all the condition for the large scale production. We go up to the 35 liter of the production, and we got a success over here. Then after the production, we need to analyze the quality of a PHA, because when we have to sell our product in market, the quality should be compete with the traditional chemical produced plastic. And you see the amount, huge amount of plastic are there. So right now, this is you can see this is the PHA granules and this is the PHA film. When we dissolve under some solvent, this look like this PHA film. So what we have to do, the utilization of agro-industrial waste as a alternative source over here uh, for the production of a bioplastic or any kind of a secondary metabolites, we can say. Then we need to scale up the studies. Then some microscopic and some other studies we need over here. Then some analysis like FTIR, NMR, DSE, TGA, GPC. These are the various instrumental analysis. Then also need to study the some tissue toxicity study. Then we need to analyze the biodegradability of this product also. So this is the property of a pH actually. Its appearance is a white to off-white and solid, and melting point can be varies from 50 degree to 180 degree, depends on the which kind of bioplastic is there. The density is around 1 to 25 gram per centimeter cube. The mechanical strength is, I can say, it depends on the type of the bioplastic which produced by the microorganism. One more thing I would like to mention that the quality of the production is depends on the type of organism we are selecting over here. Second one, the important thing, what kind of a source or nutrients we are providing to organism. That is another challenging thing, because we need to provide a constant same kind of a composition of a media for the production of a same kind of a material. So this is the most challenging thing for the production of a secondary metabolites. Then the biodegradability and the environmental properties also we need to study. And generally the bioplastic we considered, generally right now we are seeing in market the all the materials are not a biodegradable. They are claiming like that, but they are not biodegradable. But they reduce the pollution. That is the fact. The non-toxic decomposition we also need to study, like a breakdown into the carbon dioxide and the water without the microplastic formation, because right now microplastic is responsible to cause many kind of diseases, including the cancer. When we compared with the plastics, the conventional plastics like a polyethylene take hundreds of years to degrade, while this bioplastic can degrade within 3 to 6 months under the favorable conditions. The thermal and the chemical properties we also need to study. I told you also that around 120 degree it can be degrade. The biocompatibility and the biomedical property we also need to study for over here, as a because it should be the non-toxic and it must be the biocompatible, so it should be the suitable for the medical applications also. The used in tissue engineering, we can use this for the drug delivery and also the biodegradable structures also. Now, the question is the how to select an organisms. I told you the based on the type of bioplastic produced by an organism, we can choose an organism. So, generally, cuprividus nectar is used widely as an industrial strain. The Pseudomonas putida, which is produce a flexible PHA because putida generally after the genetic modifications, Bacillus megaterium produced a PHB. That was the first organism which produced a PHB. That is the good thing, and we easily isolate this Bacillus megaterium also by in our laboratory. So many of you maybe doing the dissertation work or research work, you can do the more work in this direction. So the microorganisms are genetically engineered in some cases for the improvement of pHA. So this is also one of the important aspect. The another important challenge for the production of a secondary metabolite, that is the selection of a material, a raw material, that is the source of nutrients. And we know that the carbon and the nitrogen source the most important for the growth of an organism or for the production of a secondary metabolites, because secondary metabolites generally produce in the log phase, not in lag phase. So this is the most important thing. And for that, here the PHA produced during the limitation of the nitrogen source only. So we can use the various sources like glycerol, molasses, corn-starch liquor, some lignocellulosic material like wheat straw, rice husk. Other than this, the vegetable oils, including the soybean and the palm oil, we can use, as well as we can use the methanol also as a source of carbon over here. The C1 carbon source is important for the methylobacterium organism, and it is used for the genetically modified strain. So this methylobacterium is important over here because this methylobacterium is anaerobic organism, and it reduce the utilization of oxygen. And if we are not using the oxygen, so directly it reduce the cost of production, because for the aerobic organism we need a purified oxygen, and that ultimately increase the cost of a production. So the very minute thing is there, but you when we are talking about the production, it should be considered. The nitrogen source, obviously, uh, ammonium sulfate, yeast extract, peptone, constip liquor, and the urea we can use as a source of nitrogen. But generally, the constip liquor is widely used because it have other than this carbon nitrogen source, as well as it have some vitamins also in very minute concentration, so it can be used by the organism for their growth also. So why we need agriculture waste? Generally, the agriculture waste is a very cost effective, number one. Second thing, right now we are facing a problem regarding to the disposal of some agricultural waste, and the farmers generally they burn or slash these agricultural waste, and generally it create environmental pollutions. So we can find out the some alternative source by which we can increase some secondary income for the farmers also. So this is the one of the important thing also. Why we use this waste for the PHA? Because it reduces the cost, production cost, and generally carbon source contribute the 40 to 50% of a total cost. And sustainability over here, it have a sustainability because it is a renewable, and it is a non-food biomass. So we can use this agriculture waste, and we can manage the production of the waste, because the agro industrial waste convert into the some valuable product. So sugarcane molasses, rice straw bagasse, lignocellulosic waste, fruit peel waste, liquid waste. We can use all kind of this waste. First of all, after the collection of this all the waste material, we have to pre-treat. Uh, there are the various ways are there: physical treatment, chemical treatment, enzymatic treatment. After this treatment, we have to formulate the media by using this treated waste material, and after that, the fermentation can be done, and then the organism produce a any kind of a secondary metabolite. So this pathway is a common for the all the secondary metabolite production. According to our need or our requirement, we can use the select the raw material, as well as we can select the organisms. I told you that there are the various ways are there for the pre-treatment, that is physical, in the other than the chemical, like acid treatment, alkali treatment, and the biological, like enzymatic hydrolysis. So the purpose of the pre-treatment is nothing but we are giving the opportunity to organism for the by the availability of a carbon and the nitrogen source which is present in this waste material. So the organism can easily utilize this agricultural waste, and they can grow. So the organism can break down this and convert into the simple sugar, which ultimately convert into the product. Second thing, after this, we have to do the fermentation. That is the we need some fermenter. The various capacities fermenters are there in market. You can use from the 1 liter to up to the 200, 400 liter. That is up to the pilot scale. And then in the large scale, to the lakhs of liters capacities are fermenters are there. You can use. So the microbial fermentation is a core step in the any kind of a secondary metabolite production, where the microorganisms convert the pre-treated material into the some valuable product. But after the this after the addition of a media to this fermenter, the second step is a inoculum preparation, which is a vital. We need a pure organism over here, pure inoculum. There should be the no contamination, not a single cell needed over here. If the single cell of other strain is there, it will ruin the whole fermentation process, and it directly affect the production cost. So the bacterial strain is grown in small culture flask with the rich media, and then ensure the high cell density before the transferring to a fermenter, because this is the important. We have to find out the what kind of a inoculum size should be there. It can be varies according to the organisms. Each and every time it should be checked. Then the fermentation, I told you, you can do in various size of fermenter, the 10 liter, 7 to up to the 700 liter, then to the lakhs of liter. The carbon source over here, agriculture waste like glycerol, molasses, starch hydrolysis, whatever you would like to use, you can use. Then I told you the limitation should be there in case of a bioplastic production, because nitrogen they do not need, but nitrogen needed also for their production of their some biological component like an enzyme. So it should be there, but in limited amount. The if the you are choosing the anaerobic organism, there is no need of aeration. But if the organism is aerobic, in that case, the aeration should be you have to provide. Then the all the after this addition of a inoculum and the media, organism ferment and convert to the secondary metabolite. Now the microorganism. Hello, I think some have on their mic. Okay, there are the various mode of a fermentations are there, like a batch fermentation, batch fermentation, continuous fermentation, whatever the suitable ways you are opting, you can go. But before going to this stage, you need to optimize all the things. See, when we started our production from flask to the this 1 liter of fermenter, and then to the 35 liter of fermenter. But during the fermentation, we also face some challenges, and these are we need to overcome because there are the lot of things we find. I also told you, and I would like to mention that the contamination is one of the most important, because when we are doing the fermentation, we try to produce or utilize this same kind of a condition up to the 2 weeks. But during this stage, we find some problems also. We used our own composition of a media. I'm not going to present this all the data over here, but this is the way we started with this organism, then to flask, and you can see the photograph over here. They after the recovery of a secondary metal, that is the PHA, you are seeing over here. But nowadays, I told you that there are the various companies are there. They are producing this PHA in huge amount. India over here, I am saying that started the few companies like Praj Industry is one of the most important company which produce this PHA. They are right now started the work on it. So we will see within a few years, I can say the 4 to 5 years, some our Indian product in market also. So these are the challenges we are facing. The high production cost, any secondary metabolite production we are talking, the most expensive because of the maintenance of aseptic condition, to reduce contamination chances, and the operative cost are too high, because we are dealing with things which we cannot see by our naked eye. So it is very difficult to control their behavior. So this is increase the production cost. Second thing, the scalability. Organism is behaving in a test tube, in a flask, in large scale is totally different, and because of that thing, the scalability is very challenging. The composition, as well as the I can say the competition with some other market plastic is also the challenge, because we need plastic, bioplastic cost up to the market chemically produced plastic. So it is a competition direct. Another challenge, that is the feedstock availability. When we are talking about the fermentation, the continuous media is important, and that's why the feedstock is important, and we will not get the same kind of composition in nature. So that is the also important thing. Now, the what are the future prospects? Obviously, we can overcome by utilization of a genetic engineering technique. we can modify the microbes to enhance the any kind of a secondary metabolite produced, as well as with the capacity of the we can say there are the various ways are there which reduce the cost by the genetic engineering technique, mixed microbial culture, waste based production. Obviously government policies should be the regulation should be in to promote such kind of activities, the production activities, as well as the consumer awareness. If we are not using right now also, if you go for the 1 cup of a coffee in Starbucks, okay, the straw they are providing, it is a biocompatible, it is not a biodegradable, but they cost is approximately 8 to 10 rupees of a straw, and obviously no one can afford right now. So that's why we are not using this kind of a straw, and we used the straw which is chemically produced, which is a very cheap. We are right now using. Other than this, there are the various scope are there for the improvement. The yield production by the strain, that is important. We can use the cheap material. We can develop a non-sterile fermentation technology. I told you that the contamination should be avoided for the any kind of a secondary metabolite production. So the non-sterile fermentation technique is right now is there. The few people are also working on that direction, that the non-sterile condition, how can we produce this secondary metabolites using recombinant DNA technology, metabolic engineering, as well as the synthetic biology strategies. We can modified or shell shape related genes, including the MREB, FTSA, and the SULA, as well as the enzymatic modification like a pH synthase, which alter the enzyme specificity and they enable the polymerization. So we can modify the various way, but these all are the cumulative ways. So only one way we can not stand on one. Obviously, in future direction, if we are seeing the artificial intelligence and the machine learning is a one of the most important tool for the future, and it directly give us alternative solution over here for the secondary metabolite production. So I am thankful over here for hearing me. And right now, if you have any question, any doubt, please you can ask.
Any question from any audience? Any participant? Let's see.
And if you have any question, any doubt, you can contact me directly. So for the any kind of research related work, or you can directly contact me also.
Sir, can you highlight more on the potential applications of AI and ML in microbiology?
Yes, definitely. Right now, there are the lot of work is going on in this direction, because the artificial intelligence and the machine learning, these both the things generally are working on some algorithms, utilizing the algorithms. That's why they give us some statistical ways to find out the some alternative ways of a current problem. So, for example, uh, when we are designing the drug, okay, in drug designing, right now the all the pharmaceutical industry is using this way. So this is the best example. I hope so you can understand.
Thank you, sir.
Yeah.
Sir, your email, please, in the chat box.
Sure, I am sharing my email ID over here.
Okay. Kritika, are you here? Please switch on your microphone, Kritika. Kritika, Yaduvanshi, your mic is off. Please call her. Shalini, are you there?
Yes, sir.
Please call her.
Sir,
She is
one I got a one personal direct message from the one participant that can we identify the contaminating organism and can genetically modify the organism for the production of PHA? So this is the question I got, and obviously this question is asked by the Anisha Jadhav. Anisha, yes, definitely. We can identify the contaminating organisms. We identify the organisms during the our fermentation process, which we got a contamination. And there are the various ways are there of identification, as everyone I hope so aware, as well as we can modify the genetically modify the genes of an organism for the higher production of a PHA also.
Thank you, sir.
Yes,
Um,
question, another question.
sir, they have requested your WhatsApp number and they are
Okay,
commenting
okay.
on your
I, I
presentation.
I shared I shared my contact number.
Yes, sir. Sir, can you share some insights regarding non-sterile fermentation technology?
Yes. This is the another and the latest way and the new direction of a thinking to reduce the cost of operative cost for the production of any secondary metabolites. Uh, this is actually the challenging, but right now the few are started already work by the modification of the technique. For example, if I'm just giving the one example. If we start need some secondary metabolites, XYZ as secondary metabolites, and particular organism we try to isolate from higher saline environment, for example, okay, which have a high concentration of a salt, and in this way, if example I'm giving, the 20% of a salt concentration is there, the organism only find out in such kind of a environment. We have to produce a media with a 20% of a salt. In this higher concentration, no other organisms can find out. So in this case, we can do the open fermentation. No other organism can survive because we isolated our organism in such a way that the only these organisms can found. I hope so you got some insight. Yes, sir. Any other question?
Yeah, thank you, sir. Uh, sir, please share more details about PHB production.
The PHB and the PHA both production way is the same. There is a no the thing is there, but you need to identify the organism. Number one, whether the organism producing the PHA or not. Second thing, the composition of a media is important. So these two things is there: the selection of an organism and the selection of a media. Based on that, only they produce a PHA or a PHP.
Okay, thank you, sir. Thank you so much. Sir, feedbacks are given over the chat box for you. Thank you very much.
I request Shalini to please proceed. Shalini.
Yeah, sure, sir. It is an absolute honor for me to deliver the official vote of thanks. First and foremost, my sincere thanks to our esteemed resource person, Professor Dr. D.K. Acharya, the head of the Department of Microbiology and Biotechnology, Gandhinagar Institute of Science, Gandhinagar University, Gujarat, who gave a very informative lecture on the topic Bioprocessing of Secondary Metabolites, Current Challenges, Emerging Opportunity, and Future Outlook. Then I extend my thanks to the organizing board members. Firstly, the chief patron, Professor Dr. Arvind M. Deshmukh, professor and the former head department of microbiology, Dr. Babasaheb Ambedkar, Marathwada University, Maharashtra, Government of India, the founder and All India Chairman of Microbiology Society, India. Secondly, the executive convener, Dr. Ajay Kumar Srivastav, an associate professor and the head department of botany, St. Xavier's College, Autonomous, Ranchi. And finally, the organizing chairman, Mr. Sharath, the national representative of Microbiology Society, India, who had highlighted the direction for organizing this wonderful program. Lastly, I truly thank our dearest participants who spent some time attending our international webinar today. We are very grateful to all of you. Thank you all for joining us and hope to see you all in our upcoming sessions. Thank you so much.